Hello, it's Scott Manley here, and today we have an immersive 360 video to talk about gravitational lensing. So you should be able to move the camera around, but right in front of us right now there should be a black hole, and if you saw the black hole there, you saw a ring of light around it. That is an Einstein ring. Now the gravity field of the black hole is bending the light around the edges, and at exactly the right point at that ring you're seeing, all the light is being bent around and it's focusing on a single point directly behind the black hole. So if a star is there, you will see a bright ring. Now inside there you'll also notice that this motion of the stars is kind of messed up in reverse. That's because inside that ring, in some places you're getting a mirroring effect, so the stars appear to be moving in the opposite direction. We're currently rotating in a vertical orbit, but if you look inside the Einstein ring, the stars on the left and the right are actually going in the opposite directions from the stars visible on the other side. At the top and the bottom they're still moving in the correct direction, but their motions are still distorted. Okay, for the next trick, we're going to have to drop you into a black hole. So we're going to descend feet first. If you look down, it's there just waiting for us, but don't worry, I have a lot of control over this, so I won't drop you in too quickly. Anyway, as you go down you can see the same distortions, the same Einstein ring, but if you look to the left and the right, you can see the plane of the galaxy. As we fall closer and closer, the stars begin to turn blue. This is called the gravitational blue shift. As you are falling into the black hole, its gravity field is pulling the photons down from those external sources, so they pick up energy. So the red photons get shifted towards blue photons and everything starts to look blue. Now we're sitting just above the event horizon, and the only way we can see the universe is a point of light above us. But thanks to my godlike powers, I will be able to pull you back out despite the crushing forces of gravity. As we come out, note again, the stars begin to change back from blue through to their normal colours. Now the opposite is true of light escaping from near the black hole. That light has to travel upwards against the gravitational force of the black hole, and in so doing it loses energy, and so it will change from blue towards red, and this is called the gravitational redshift. And now we are orbiting the black hole. We are orbiting at a distance of 3 times the Schwarzschild radius. Now the Schwarzschild radius is a really important number. It's defined by the mass of the black hole, and the important thing to know is that the Schwarzschild radius is the event horizon. That's the point of no return. But at 3 times that distance, that's the innermost stable circular orbit. This is the point at which you can have a stable circular orbit, but below this it is no longer possible to orbit on a stable circular orbit. There are possible other versions, but your orbit is highly likely to be unstable, where you will either get kicked off to infinity or fall into the black hole. At this perilously close altitude, the Einstein ring has become an Einstein horizon. Also, the stars outside are blue shifted. But I'm going to point out that this simulation is missing the Doppler shift, so the stars that we are moving towards should be blue shifted, and the stars we're moving away from should be red shifted, and it should be quite substantial, because when you are this close to the black hole, you are moving at a significant fraction of the speed of light. Thanks to my godlike powers, we can get even closer to the black hole. This is just outside this photon sphere. That is the region where you have to be moving at the speed of light to orbit the black hole. And yeah, there's normally no stable orbits for physical things at this distance, but again, I've got you covered here. So yeah, now we see the horizon around us that is the Einstein ring, and then there is just the dark blackness of the black hole beneath us. I've got this set up with an orbital period of about 30 seconds, which would imply that this is a supermassive black hole with hundreds of thousands, maybe even 1 million solar masses. Now, many black holes are much smaller, maybe 4 or 5 solar masses, and for those, the orbital period would be measured in fractions of a second. So again, let me use my godlike powers to reduce the size of this black hole, and therefore increase the orbital period so you can get an idea of what it would be like orbiting a black hole that maybe was only about 100 solar masses, where the orbit period is a fraction of a second. Yeah, I hope you aren't doing this in VR, or if you are, I hope you've got a sick bag sitting around nearby. The black holes I've showed you so far do not have accretion disks, so you could see the stars around them. Once you add the accretion disk, the light that's coming off it just overpowers everything else that's there. But it does provide an interesting reference point for these flypaths. Now, if you look around you, you can see the edge of the disk kind of at a certain level, but as you fly over the top of the black hole, the whole disk lifts up around you, because at that point, if you imagine, the light from the edges has to get curved down towards you, so everything seems as if it's being lifted up when you're in this, when you're sitting on top of this black hole. And of course, once you have an accretion disk, you also should be thinking about redshift and blue shift, which means one side of the accretion disk would actually appear brighter than the other. Regardless, I hope you found these visualizations interesting. You can get them with Space Engine, it's all free on the internet. I'm Scott Manley. Fly safe.